of a hypothesis test in the confidence intervals. When we wanted to take a confidence interval and find the interval, we used PANIC. So PANIC, which was the parameter of interest, the three assumptions or conditions, the name of the interval that we were running, and then the actual interval, and then our conclusion. So with hypothesis testing, we're going to use phantoms. And we've gone through what it stands for. I'm giving you the sheet of what it stands for, and then you've got to, you're going to have to go through it a little bit. But phantoms is, P is the parameter of interest, just like it was in the proportions, in the confidence intervals. H, though, stands for hypotheses. So when you're running a test, you actually have what's called a null and an alternate hypothesis. So we're going to go over that in just a minute. And then you still have your three conditions, and they're the same as they were in the intervals. So that's good. Then you just have to name your test, what your test is. You can give the test statistic from the calculator. So we'll talk about what that is. O stands for obtaining a p-value. So a p-value is the probability of us getting the results we got, or even more extreme, and one of the hypotheses being true. So we'll talk about it as we go through it. It'll make more sense. The p-value that you get from the calculator will help you to make the decision in M. And when you make the decision, then you just state your conclusion. Okay? So those are the steps. It's not necessarily longer than a confidence interval. It's just more little parts that go through it. So we'll take the first problem. It says, any basketball fan knows that Shaquille O'Neal, one of the NBA's most dominant centers of the last 20 years, always had difficulty shooting free throws. Over the course of his career, his overall free throw percentage was 53.3%. During one offseason, Shaq had been working with an assistant coach on his free throw technique. During the next season, a simple random sample showed that Shaq made 26 of 39 free throw attempts. Test the claim at the 0.05, and the SL stands for significance level, so 0.05 significance level, that Shaq has significantly improved his free throw shooting. So, important parts in this problem right here is that his overall free throw percentage was 53.3%. That's important to have. The 26 out of 39 that he's done this year is very important. And then the last sentence, we're testing to see if he significantly improved it. So it tells us what direction we're testing for. Okay, so all three of those things are going to be important as we go through. And then the significance level that we're running the test at. All right, so let's go to the actual, so we'll go to those, to the 4-step or the 8-step process. So first is the population, we said is the population parameter. So the parameter of interest is the true proportion of free throws Shaq makes, right? So we're really interested in the true proportion of free throws that he makes. Now, the true, or so over time, the P is 0.533, right? 53.3%. That's an actual, that's a population. That's from all of his career. Now, our sample that we got here is P hat. That's our sample, is 26 out of 39, which is 0.666, right? And repeat it. So we got 26 out of 39 that he made in our sample for the next year. So we've got the true proportion of free throws that Shaq makes is our parameter of interest. That's what we're interested in. We see the true proportion, or what we think is the true proportion from his career, and then we see what he made from that next season after he had help from the coach. Now, this is a new part. So hypotheses, you never have that in confidence intervals, but you always have this in hypothesis tests. So no matter what test you're running, you're going to write this. You're going to write HO and HA. So HO stands for the null hypothesis, and that means the hypothesis that nothing has changed. Null means none. So basically, nothing is different. That would be the null hypothesis. That would be that nothing has changed at all. Okay? And then HA is called, it stands for that, A stands for the alternate hypothesis. That means what the problem is asking about. Okay? So HO is always going to be an equal to. So the null hypothesis is that the proportion equals, and it's what happened throughout his career. It's just the normal proportion, 0.533. Okay? So the null hypothesis is that P equals 0.533. Now, the alternate hypothesis, the number has to be the same as your null hypothesis. So you have to be looking at the same number. You have three options when you're doing an alternate hypothesis and you get it from the problem. You either do less than, greater than, or not equal to. Okay? Now, if the problem doesn't tell you what direction you're going in, then it's not equal to. And you're looking for both, right? If the problem says we want to see if it goes lower, then we do less than. If it says you want to go higher, we do greater than. So in this problem, which one are we doing? Less than, not equal to, or greater than? Greater than, because it says at the end, did he improve his free throw percentage? So we're testing to see if the proportion improved. So that means that P would be greater than 0.533. Now, we know it improved, but did it improve significantly enough to say that he's better? Or do we need a bigger sample size or whatever? Okay, so greater than is our alternate hypothesis. Now, you have to look at the problem, these problems, to tell if it's a not equal to, a less than, or greater than. All right, assumptions and conditions. So those we don't have to remember that. One is random. So it says a random sample. It said a random sample of 39 free throws. Right. Number two is independent. We assume he shot more than 390 free throws. And then lastly, we go to normal. Now, with normal, you need to make sure you go back. Now that we're thinking about it, we need to go back and make sure the normal condition for proportions, remember, is NP is greater than or equal to 10, and N1 minus P is greater than or equal to 10. Now, these are from our sample. So in our sample, 26 is greater than or equal to 10, and then he missed 13, right? So 39 minus 26 gives us 13, so we check that out. So it passes the random, independent, and normal condition. Remember that if you're dealing with proportions, you do the NP greater than or equal to 10, N1 minus P greater than or equal to 10. If we were dealing with means, like we did just recently in the intervals, then we would have been talking about the central limit theorem, that the sample size has to be at least 30. But if we're dealing with proportions, we have this one, NP and N1 minus P. All right, so in N, all we have to do is name the test. So this is a one proportion Z test. And then in T, it says test statistic or confidence interval calculated. And you do not have to display the formula on this. So have that in there. That's extra, so we don't have to do that. We're definitely not going to go beyond right now. So the T is the test statistic, and the O is called the p-value. So the T, the test statistic, will actually be the z-score, okay? And remember, the z-score tells you how many standard deviations you are away from the mean. So the bigger your z-score is, the more significant a result you're going to get because the further away from the mean you are, okay? So we get to the point after naming the test, just like we did in PANIC with the confidence intervals. Once you get past the naming of the test, then you get to where you're going to go to your calculator. Okay, so we're going to go to our calculator and we're going to enter this information. So on your calculator, you want to go to stat test. Now, you should have completed all the ones from 7 below were in intervals. Now we're going back to get 1 through 6. Okay, so now we're looking at the proportion tests you see are number 5 and 6. So we're looking at a 1 proportion Z test. So the first number is asking you see that little O beside it, that's the null hypothesis. That's basically what it was in his career, right? So that is the 0.533. The X is from our sample, so 26 out of 39. And then you look at the next line, you see either a not equal to, a less than, or a greater than. That's what is your alternate hypothesis. Our alternate is that it's greater than 0.533. And we can then go down and hit calculate. Okay, I'll show you what draw is in a minute, but calculate. So to calculate, there we go. We get a z-score of, and you want to go to 2 decimal places, we get a z-score of 1.67. And we're going to get, this is important, this is not the proportion, this is called a p-value of 0.0471. It's going to be 4 decimal places, so I'm going to get there in a minute. But the z-score is important right now, so it's the test statistic. It is 1.67. Okay, that's how far away from the mean his shooting actually was. So 1.67. And now I'm going to erase and kind of scroll down to the last part. The p-value, the z-score, like we said, was 1.67. The p-value was, so the p-value is 0.0471. Now, that is that has nothing to do with the proportion. The p-value is the chance of us getting the results we got, or even more extreme, and the null hypothesis being true. So the null hypothesis is just that nothing's changed. So if you get a really low p-value, it means that the null hypothesis being true is really low, which means we're probably going to end up saying that the alternate is true, that the alternate happens. The null hypothesis is that things have stayed the same. So if the p-value is really low, then the probability that things have stayed the same is really low, which means we're able to say that something's different. Okay? So again, the p-value is the probability of us getting the results that we got, or even more extreme, and the null hypothesis still being true. Okay? So the lower that p-value is, the more confidence we have that the null hypothesis is not true. All right. Now, making a decision is based on the p-value that you got there. Now, I will show you that in the drawing part on your calculator. So if you go to stat test and you go to the 1 proportion z test, instead of hitting calculate, you can hit draw. And what it does is it draws the normal curve and it shades the area where the null hypothesis might be true. Okay? It shades it. So see how you get a z-score that's almost 2 standard deviations above the mean, and it's shaded greater than, so it's shaded right in this area. The area that's shaded is 0.0471. So it's very easy to, and they put that in part O to draw that. All you have to do is show a picture with the region. It says, here you go, there's that, right? There's our normal curve right here. This is a P of 0.0471, and it's shaded all in here. They'll look better when you shade it, and it's not me on the board there. But that shows that little area where the null hypothesis could still be true. Now, for M to make our decision, you are looking at the significance level of 0.05. So you say, because the p-value, and this is going to be a sentence we use every time, because the p-value of 0.0471 is blank than 0.05, and you're going to fill in the blank, obviously, okay, so because the p-value of 0.0471 is then 0.05, we HO. So if the p-value is less than 0.05, you reject the null hypothesis. If the p-value is greater than 0.05, you don't accept it, you fail to reject it, meaning that there's a greater than 5% chance that it's still true, but that doesn't mean that we accept that it's true. It just means we don't have enough evidence to say that it's not true. So we either are rejecting this thing or we're failing to reject it. It's kind of like you still believe, you can compare it to like a courtroom. You still believe the person's guilty, but you don't have the evidence to fully prosecute them. So it's not that you are accepting that the null hypothesis is ever true. You're either rejecting it or you're failing to reject it. Okay. So in this one, 0.0471 is less than 0.05, so we reject HO. That means we reject the null hypothesis because it has a less than 5% chance of actually being true with us getting the results we got. If there's a greater than 5% chance normally, depending on the significance level, whatever the significance level is, if there's a greater than 5% chance of it being true, then we will say, okay, then we will fail to reject it because it still has a pretty good chance of being true. Now, that's our decision. Our decision comes directly from the p-value, and you compare the p-value to your significance level. That's how you make the decision every time. Now, this is in the context of the problem. So we rejected HO. That means there is sufficient evidence to suggest that, and then you look at the last sentence of the problem. Shaq has improved his free throw shooting. Now, here is so again, that's the alternate hypothesis, right? Is that it's greater than 0.533, which means he's improved it. So, here's, again, we make the decision. The decision is because the 0.0471 is less than 0.05, that means the chance of the null being true is less than 5%. We reject the null hypothesis, which means that we're rejecting HO in favor of the alternate. The alternate is that it's greater than 0.533, which means that he improved his free throw shooting. So there is sufficient evidence to suggest that Shaq has improved his free throw shooting. Notice, we don't use definitive words like we know that he has improved his free throw shooting, or we can prove that he has improved his free throw shooting, because we can. So you always use sufficient evidence to suggest, because we're just taking a sample and getting this. So we don't know for a fact that he's improved, right? But we do see that there's evidence to suggest that he has. Now, if the p-value would have been greater than 0.05, greater than our significance level, we would have said we failed to reject HO. And if you fail to reject it, that means you just got to go with what the null. So you would say there is not sufficient evidence to suggest that he's improved his free throw shooting. So in that second sentence, you're always talking about what the alternate is, what you're trying to prove. Either there is sufficient evidence that happened, or there's not sufficient evidence to suggest it. Okay? Just like you either reject the null hypothesis or you fail to reject the null hypothesis. If you reject it, then you had sufficient evidence. I think about it like this. If I'm sitting here, if I reject something that you say, for me to reject it, I have to have sufficient evidence. Or otherwise, then why would I be rejecting it? If I'm rejecting something, then I've got to have evidence to reject what you say. If I don't have evidence, then that doesn't mean I have to agree with what you say, but I'm just going to fail to reject, meaning I can't reject it because I don't have evidence to prove what you're saying is wrong. Okay? If you reject something, you better have sufficient evidence, right? And if you fail to reject something, you don't have sufficient evidence. Now, another way of remembering the p-value, a lot of AP Stats teachers say this, so I'll say it, it's not a big deal. They use it. They say, because HO, a lot of students see HO and they don't see that it's the null hypothesis. They say, oh, that's Hove or something. Hove and Hobb, right? So the little slogan they came up with was, if the P is low, reject the Hove. Okay? And if you can remember that, then you know what to do. Yeah, but people would mess it up every time. So if you remember that little trick, you'll never mess it up, right? So if P is low, reject the Hove. So what that means is if P is below the significance level, you reject it. If P is above the significance level, you don't. Okay? And that's because the p-value is the probability of the null hypothesis being true and us getting the results we got or even more extreme. All right, so I tried to explain it as best I could with that. Quick, we can do this. 2 Polish math professors and their students spun a Belgian euro coin 250 times. It landed on heads 140 times out of those 250. One of the professors concluded that the coin was minted asymmetrically. A representative from the Belgian Mint said that the result was just by chance. Is the math professor or the representative from the Belgian Mint correct? So is it a fair coin, or is it weighted on one side or the other? Okay, so is it fair or not? So it says, test the math professors claim that the coin is not fair. Okay, so one of the professors said that can't happen. That it's got to be that the coin's not right. And the Belgian Mint company said, no, it's right. The coin is fine. It will land 50-50, heads or tails. All right. And it says at the 0.01 significance level, test the math professor's claim that the coin is not fair. All right. So let's go to what we're interested in. We're interested in the true proportion of what? True proportion of times it lands on heads, right? Of heads for the Belgian coin. Okay, and the P, this is kind of tricky here. The P would be like what we assume is true. We assume that it lands on heads how often? 50%, right? So 0.50. In our sample, we got it landed 140 out of 250, okay, which is 0.56. That's what we got in our sample. we assume that it's 50%, but in our sample, we actually got that it was 56%, which is why the professor said that. Now, assumptions, well, no, I got to go back. So that was our parameter of interest, the proportion of heads. And now you want to go to the next part, which would be your hypotheses. So your hypotheses are going to be HO is the null hypothesis. That's that the true proportion is 50%. Now, HA is our alternate hypothesis. Now, in the problem, it says, is the coin fair or not? It doesn't say in what direction. So it actually doesn't tell us whether to do less than or greater than. It just says they want to know, is the coin fair or not? Okay, so we're testing to whether it is fair, that it's 50-50, or it's not fair. So that the null hypothesis, or the alternate hypothesis, is that it does not equal 50%. So there wasn't a clear direction. It didn't say we want to test to see if there's more heads or more tails or whatever. It just says, is the coin fair or not? All right, so we got our assumptions and conditions. Number one is random. So we need a random sample of 250 tosses, I believe. Check. Number two, independent. Assume more than 2,500 tosses. Okay. Number three, normal. NP is greater than or equal to 10. N1 minus P is greater than or equal to 10. We had 140, and then 250 minus 140 is 110. So our sample is big enough. So the random, independent, and normal, the three conditions, it passes really quickly. The name, again, is fine for now, but as you learn more tests, then it gets to be more important. So one proportion z-test. So you get through the first part pretty quickly. And then you're saying, all right, I got the calculator. So that's kind of your goal, is once you get through naming it, once you've got the correct name, then you should be able to go into the calculator and get the correct statistics. So remember, what you're getting from the calculator right now is the test statistic, which is the z-score, and the p-value. So if you go to draw instead of calculate, you can actually get the test statistic and the p-value and the graph all at once. Okay? So let's go to our calculator, and we're going to go to stat. You're going to go over to test. You're going to go to one proportion z-test. .5 is our null hypothesis. We got 140 out of 250, and we want to see if it's not equal to. Okay, and I can go ahead and hit draw. Now, if you notice, this one's going to be shaded in both tails. That's because it's a not equal to, right? Because since it wasn't a less than or greater than. If it's a greater than, it's only shaded in the upper. If it's a less than, it's only shaded in the lower. This one we're just seeing if it's not equal to 0.50, so it's going to be shaded in both directions. Okay, so we get the next thing is the T. It says test statistic. That's the z-score. The z-score is 1.897, so that would round up to 1.90. Z-scores, you typically round to 2 decimal places, and then p-values go to 4. So z-score is 1.90. O is obtain the p-value, step O. The p-value is 0.0578. And then we can make our little drawing, right? With 3 standard deviations. Notice the z-score is right near about 2 standard deviations. That's where you're shading. So from here and from here. So you shade in both directions. And remember, that's your that gives you your p-value of 0.0578. Those come from here and here. Okay, so that is your test statistic and obtaining your p-value. So we should be on the M and S part at this point. So we're looking for the true proportion of heads for the Belgian coin. We assume it's 50%. In our sample, we got 140 out of 250. The null hypothesis is that it's 50%. The alternate is that the coin's not fair, so that's not 50%. We know it's random because we took a random sample of 250 tosses. We know it's independent because we can assume that we can make more than 2,500 tosses. We know it's normal because the probability or the number of successes we had was 140, which is greater than 10. The number of failures we had was 110, which is greater than 10. So we run a 1 proportion z-test. We get a z-score of 1.90. We get a p-value of 0.0578. There's where it's shaded. There's the proportion, the 0.0578. And now we're ready to make our decision. So we go down to M and S, which is make the decision and state the conclusion. What's in this problem and the first one, first of all, is that we are looking at 0.01 is our significance level. So we're going to say because the p-value of, what was the p-value again? 0.05 what? 78 is greater than 0.01 because we compare it to our significance level. So last time our significance level was 0.05. This time it's 0.01. And think about it. The 0.05 significance level is about the same as having 95% confidence. It's like a 95% confidence interval. The 0.01 significance level is like having 99% confidence. It's like a 99% confidence interval. So because the p-value of 0.0578 is greater than 0.01, what do? You fail to reject HO. Okay. Now, because we wanted there to be, think about it, if the significance level is 0.01, we wanted there to be a less than 1% chance of the null hypothesis being true and us getting the results we got for us to reject it. We wanted there to be a less than 1% chance. But there's actually almost a 6% chance of it being true. Now, that still means it's probably not true, okay? Because that doesn't mean we're going to say, yeah, we accept it. It means that there's too much of a chance, though, of it actually being true. So we say, because the p-value of 0.0578 is greater than 0.01, we fail to reject HO. That means there is not sufficient evidence to suggest that, and then you think about what is your alternate hypothesis saying? It's saying that it's not equal to 50%, which is that the coin's unfair, right? So there's not sufficient evidence to suggest that the Belgian coin is unfair. So because the p-value of 0.0578 is greater than 0.01, we fail to reject HO. So we are not able to reject it. If you're not able to reject it, that means you did not have sufficient evidence in the alternative. So if somebody tells you something and you're not able to reject it, it's because you don't have sufficient evidence in the alternative. Okay. It doesn't mean that we accept that the null is true. It means that we failed to reject it. We didn't have enough evidence. If our p-value is low enough, we're able to reject it, which means we have evidence. If our p-value is not low enough, We're not able to reject it, which means we don't have evidence. Fail to reject means no evidence. Rejecting means evidence. All right. So you look at number 3, you look at a random sample of 300 patients. 21 of those experienced nausea. The drug manufacturer claims that fewer than 10% will experience nausea. So there's your null and alternate hypothesis. You're looking at 10%, right? Of patients who take its new drug for treating Alzheimer's will experience nausea. Test this claim at the 0.05 significance level. So we're testing if it's less than 10% at the 0.05 significance level. All right, number 4, a survey claims 9 out of 10 doctors recommend aspirin for their patients. That means 90%, right? So the survey says 90% of doctors recommend aspirin for their patients with headaches. To test this claim, a random sample of 100 doctors is obtained. Of these 100 doctors, 82 indicate they recommend aspirin. 82 out of 100. Is this claim accurate? So the claim is that 90% recommend aspirin. The question is saying, is that claim accurate? So it's like, so it would be not equal to 90% is what we're testing for. Does it say, is it less than or greater than? It just says, is the claim accurate? That's what we're trying to find out. And in that one, again, it says, use the alpha level of 0.05, which is the significance level. So in both 3 and 4, the significance level 0.05 is what you test your p-value against. That's what you see if it's greater than or less than in order to do your conclusion. Okay, so you're going to run through those. If you have any questions, you can let me know for the 2 1 proportion z tests.